What's up, people? My name is Emmanuel Williams, and welcome back to the tutorial on multiple expansion. So, this problem statement is the most interesting of all problem statements so far because now we have a very challenging problem. You are given the fact that the electric field of a pure dipole is actually given by this. You have a delta function term cropping up because we haven't done this differentiation properly. I mean, we assumed a few things which aren't really right. So to set things right, we're going to go to an equivalence system and get back to this. For the first thing first, you take a solid sphere with a surface charge density sigma equals sigma naught cos theta, and we're going to solve the Laplace potential, the Laplace equation for that. So this is how my sphere looks like. The n cap is r cap, which is the normal to the surface of the sphere. Theta is the polar angle. So we are going to derive the solution for the Laplace equation, and the charge density of sigma is given to us. And since we are in the polar coordinates, we very well know that the solution is of this form: AL r power L plus BL r power L plus 1 PL cos theta, where PL is the Lth order Legendre polynomial with cos theta as the variable in it. And then the AL, BLs are various constants depending on the boundary conditions and all. So V, the total potential, is the linear combination of all VL from L equals 0 to infinity. So first thing first, we introduce the finiteness condition. Finiteness means that potential has to be a finite valued quantity. For R less than R, I want a finite value, which means for R equals 0, I want a finite value. So all BLs go to 0, so I'm left with AL R power L. For R greater than R, I want all potentials to vanish, which means all ALs go to 0. So you're left with the BL term. So this is one condition. Then you have the condition of continuity at capital R. So BL at R plus, which is the one coming from the BL term, should be the same as BL at R minus, which is the one coming from AL term. Since the PLs, since we are equating the VLs term by term, PLs are same on both sides. So you are finally left with AL capital R, actually. Capital R for 2L plus 1 equals PL. So this is the condition for continuity. And then this is the electrostatic boundary condition. So del V by del R. So minus del V over del n cap, the directional derivative along the outward normal. The negative of that gives me the electric field. So the difference of the electric field between the interfaces gives me sigma over epsilon naught, which is the electrostatic boundary condition. So we're going to evaluate this directional derivative because n cap is the same as r hat. We can simply replace n hat with r. So that's how we do it. And we have to evaluate this derivative on the two ends, on the two inner and the outer surfaces. So when we do that and go about solving this, you do notice that the Legendre polynomials are orthogonal. So it's like this. I can basically think of the Legendre polynomials as a basis. So I can equate these quantities term by term. So on the right side, it was sigma naught cos theta over epsilon naught. Now, sigma naught cos theta can be written as P1 cos theta. If you remember back from our first video where we saw how we could replace P1 cos theta as cos theta. So, and on the left hand side, you notice that there is a series with PL involved. On the right hand side, you have just one PL, which is P1. So basically, there is no contribution coming from the other PLs except P1. So all the coefficients, all the ALs and BLs for L not equal to 1 should be 0 because the Legendre polynomials are orthogonal. So we are equating the coefficients term by term. So this happens for all L not equal to 1. But when L is equal to 1, you get the condition 2L plus 1 AL R power L minus 1 PL cos theta equals this. So 3A1 P1 cos theta is sigma naught over epsilon naught P1 cos theta. So that gives me A1 as sigma naught over 3 epsilon naught, B1 as sigma naught R cube over 3 epsilon naught, and everything else is 0. So this is the final solution. And notice that I have replaced R cos theta for R less than R with Z because that is the Z component or the Z coordinate. You will find that you will see the significance of that later on when we go with the electric field and the interpretation associated with this. So when you compute the electric field, we just need to take the gradient. So for R less than R, since I've written R cos theta as Z, I'm going to take the gradient using Cartesian formula. And for R greater than R, I'm going to compute the gradient using the spherical polar formula. When you do that, you observe that the electric field inside the sphere is a uniform electric field directed along the negative k direction, assuming that sigma naught is positive. And so if you look at the expression for R greater than R, it doesn't seem friendly enough. You have an R hat and a theta hat term. So we're going to do a little bit of manipulation. First things first, we're going to do this small bit of a manipulation here. Sigma naught R cubed by 3 k hat. I'm going to write this in terms of dipole moment. And when you do that, you get this. Sigma naught over 3 k hat is T over 3 tau R, where tau is the volume of a sphere of radius R cubed. There's a reason why we are doing this, and that will come out to be evident later on. And this is a little bit of a mathematical exercise you guys might want to try and convince yourself that this actually holds. But when you come to the end of this mathematical exercise, you're finally left with this expression, this familiar result from our previous video, the electric field of the dipole. And this is the electric field outside the spherical, outside the solid sphere. But what is the electric field inside the solid sphere? It's P over 3 epsilon naught tau R. So what we should understand here is that as the radius of the sphere decreases, when we keep the dipole moment constant, we are approaching the dipole behavior more or less. So what happens when we replace this with a perfect dipole? Then the electric field blows up at a small point. It blows up because of this volume term shrinking down to 0. But this blowing up is concentrated to one small point. And so this kind of indicates that there might be a delta function of some sort. So to bridge that inconsistency, you introduce a delta function, and so you get this. Well, I'm pretty sure for starters that this argument won't be a very convincing argument, given that it sounds vague and all. Yeah, it is. I mean, how did you get from here to the delta function just by letting R going to 0 and making all that hand-waving statement? Well, for that, let's get back to this. Let's integrate the electric field with respect to volume. Let's integrate the electric field over all space. Let's find the volume integral of this, and you just need to work it out a little bit. Basically, P dot R hat is nothing but P cos theta, and then when you integrate R hat with respect to phi, you are left with 2 pi k hat cos theta, because the one which the planar component